Today I'll be talking about the use of calculus in real life. So first, who invented calculus? The direct origin is unclear, but the consensus is that calculus is Sir Isaac Newton's and Gottfried Wilhelm's invention. Fun fact, it's said that Isaac Newton actually invented calculus, or the concepts or notions of it during the bubonic plague. The idea of infinitesimals and infinity were existent prior to the 1600s in different societies. Philosophers who study all areas of studies got interested in the idea of infinity, and the two scientists invented variables, formulas, and ways to use the concept during their lifetime. There are lots of uses to calculus, which is why it survived until today. What parts of calculus are being used in real life? Fundamentally, there are two halves of calculus, which are derivatives and integration. Meteorology, predicting the weather models, search engines, architecture, and they're almost always used to make prediction models. For example, in architecture, they need to know how to make structurally sound buildings. So they use calculus to find out at what point would the building topple over, and they have functions related with that. Why was calculus invented? Well, there's not a reason calculus was invented, but it has a purpose, which is to study the rate of change using knowledge of infinitesimals and limits. It is used today because it allows people to calculate the rate of change at a certain point, or the area under a graph. You use derivatives to find the rate of change or slope at a certain point, and integrals to find the area under a graph. Many phenomena or scientific happenings can be graphed, and knowing the slope can allow them to make a formula. Scientific happenings, weather is a part of natural occurrences, and amount of rainfall can also be graphed, and the relationship between time in years and the rainfall can be calculated, and calculus can also be used to analyze a graph and to make a rainfall formula. It comes in handy when making a reasonable prediction about the future. And now we'll be looking into examples of calculus in different areas of study, such as weather models, public health, architecture, physics, chemistry, and biology. So first of all, weather models. There was something called numerical weather prediction in the 1950s, and this wasn't calculus related, which means that it was less specific and it was harder to make accurate predictions. But then a new system in the 1970s came up which used calculus, and it allowed people who studied weather to make more accurate predictions about the future based on probability and past trends. Multiple variables in weather were considered, such as amount of rain, the season, the time, the temperature, or the climate, or past trends, how much rain was fallen during fall, summer, winter. But the more the variables were, the more complex the calculation was. That meant that people had to use supercomputers to find out trends, because weather isn't just about one factor, or like amount of rain and time. It also puts into account temperature and all those other variables. And the more the variables are, the more equations and formulas have to be used. That's why it was the more complex the calculation was. So now that the coronavirus is rampant, the knowledge of calculus can be used to improve public health and help countries find out effective measures for their countries. So if we are to graph the number of people infected over the time or the days since the first infection, then we can see that there's an increasing trend, as we can see for most countries. Measuring the slope of that graph would show us the infection rate. What that means is just a number or a rate that shows how many people were infected over a certain period of time. Now that can be calculated using the knowledge of derivatives if the equation of line of best fit is to be derived from the graph, and that function is differentiated. The slope can be found on any point of that graph, and this allows people to respond to how infection rate changes over time, and help put effective measures for diseases such as the flu or the common cold. The infection rate isn't as high as the COVID-19, because we can know that because we know knowledges of slopes, and slope can be found out using calculus. If the slope is less steep, it means that the infection rate is lower. If the slope is steep, like we see in COVID-19 graphs, then it means that the infection rate is high. We wouldn't need a lockdown for people for a disease that have a less steep slope than one that has a steeper slope, such as COVID-19. So for architecture, calculus is also used because they need to find out how much weight the buildings can hold, or how weirdly they can shape the buildings before it collapses onto itself. And it's used in structural engineering because of the exact reason. And calculus is used to calculate the balance of weight when making bridges and other structures. If a bridge has a curve over here or over there, and it's in a place where the weight can't hold, then they use calculus related calculations to find out which place it can hold and which place it can't hold. And structurally sound buildings are easier to make with a knowledge of calculus because they know how much the building can hold before it collapses. So even in a subject like chemistry, calculus is used. In chemistry, there's something called radioactive decay, and it shows the decay of radioactive particles or substances over time. That's also a relationship of between how much the mass of the substance decaying over time. And using calculus, we can find out the rate at which decay is occurring, and we can find the reaction rate from time taken to use the reactant. So, for example, if we have a reaction and it takes 5 minutes to use up all the reactant, and there are a certain number of mass, we can use differentiation to find out the slope. And if the slope is steep, it means that the reaction is happening at a fast rate. And if the slope is less steep, it means that the reaction is happening at a lower rate. In physics, there's a lot of math included for various topics, but one of the most prominent examples of where calculus is used to find different functions or formulas that are used in physics is kinematics. Kinematics is a study of objects in motion, so obviously it will include things like velocity, or more commonly known as speed, even though they are different things, acceleration of an object, and the position of an object. And the the functions of each velocity function, acceleration function, and position function that can be expressed in equations like ax equals x squared plus 2x. It can represent the acceleration over time, velocity over time, and position over time. But calculus is used when we want to make new formulas from the formulas we already have. So SUVAT formulas, which are used to calculate velocity, acceleration, displacement, initial and final velocities, and time. Most of the formulas are derived from integrating or differentiating formulas that are already present, like such as velocity times equals distance. Integrating that function will give another function or formula that could be used to find out answers to a certain problem, which is used in real life. Even in the quantitative side of biology or medical science, calculus can be used. Calculus is generally used in qualitative data, which shows visible qualities, but in quantitative ones, where it's usually surrounding numbers, it can be used extensively. For example, if there's a bacterial or viral population change, it's still related with the time it took for the population to change. So again, since calculus is the study of rate of change or relationship between two variables, it can also be used. If you look at the graph on the left, it shows the population growth graph of the world over time, and we're not on 2015 or 2150, but we still have there's prediction made on what the world population would be. And how people do that is they use the knowledge of calculus that they have and slopes a graph, and they model it and see what the chance would be that the world population would be at a certain number. For example, it would be a really low chance that the world would be at zero, looking at the increasing trend. And since the increasing trend is close to exponential, the supercomputers take a lot of things into account when calculating or predicting that. And this is how it's used in studies like on population studies and in biology or medical science. And in conclusion, calculus is just the study of change, and there are two halves of calculus, which are derivatives and integrals. And it's usually used to predict the future and to model relationships and to find out what will happen next. What is the trend in different relationships of various variables in weather or biology or chemistry? It's not used to do qualitative data analysis. It's used to do quantitative data analysis where people are playing around with numbers, looking at change of numbers, because qualitative data can be analyzed not only with calculus but with other fields of study. But since most fields of sciences or studies are looking at the rate of change or how different things are changing over time, calculus can be used when it comes to dealing with numbers. And it's needed for all sciences or fields of study when they're dealing with numbers. These are the links to the images that were used in the slideshow. Thank you for listening.